The physical record of 202 combat missions is written in structural deformation. This is the Martin B-26 Marauder designated Flak Bait. Operating for nearly 2 years in the European theater, this specific airframe sustained massive structural perforations. To maintain flight capabilities, ground crews prioritized rapid return to service over aerodynamic perfection. The result is a dense patchwork of overlapping field-applied aluminum repairs riveted directly over the factory skin. The preservation of this aircraft at the Mary Baker Engen Restoration Hangar at the Stephen F. Udvar Hazy Center requires a strict operational constraint. The objective is not to restore the bomber to factory-new condition. The objective is to stabilize the original damage, field patches, and operational dirt, preserving the bomber as a forensic time capsule. In conventional aviation restoration, the engineering baseline is often operational completeness or a pristine static display. Damaged sections are replaced, corrosion is removed, and paint is reapplied to match factory specifications. Flak Bait reverses that logic. Credited by the Smithsonian with 202 combat missions, the bomber derives its historical value from the structural imperfections that record repeated survival over Europe during the Second World War. Removing them would destroy the evidence. Mapping the damage defines the scope of work. During its service, the bomber was struck and repaired again and again, leaving more than 1,000 patched combat holes across the artifact. These were not uniform punctures. Impact energies warped adjacent aluminum frames and sheared factory rivets. Shrapnel could sever hydraulic lines and electrical bundles. On 2 separate occasions, the aircraft returned to base operating on a single engine. Each visible repair from these events forms a chronological layer. Wartime maintenance teams cut crude patches from available aluminum stock and drove new rivets into stressed skin under operational pressure. When a high-velocity projectile tears through an all-metal stressed skin structure, it disrupts the continuous load path. The metal skin no longer carries tension evenly across the airframe. To prevent catastrophic failure during subsequent flights, ground crews often drilled stop holes at the ends of jagged cracks and overlaid new aluminum sheet metal. These field patches could vary from the original factory skin in thickness, fit, and finish. The uneven stiffness created localized stress concentrations around the new rivet lines. The conservation team must now analyze these stress points. They are not merely visual artifacts, they are permanent alterations to the structural geometry of the aircraft. Preserving this geometry means accepting a weakened airframe and designing support methods that do not force the compromised wartime structure back into a factory ideal. The transfer of all components to the Udvar Hazy facility in 2014 initiated a rigorous condition assessment. Conservators faced a machine composed of overlapping materials, each degrading at different rates. The aluminum fuselage exhibits localized galvanic corrosion where dissimilar metals were joined in the field. The rivets holding the wartime patches have oxidized. The operational grime, composed of engine oil, hydraulic fluid, carbon exhaust, and dirt from unimproved European runways, has bonded directly to the exterior paint. This introduces the core mechanism of time capsule conservation, stabilizing the existing layers without changing their visual or physical properties. The team applies treatments to arrest degradation in place, locking corrosion, dirt, and paint history into their current condition. Every physical anomaly is treated as an intentional modification or a direct result of combat operations until testing proves otherwise. Instead of finding defects to correct, the team finds defects to protect. The structural analysis focuses entirely on determining if a damaged section is currently actively failing or simply static in its deformed state. Structural gaps remain open if they were open at the end of the war, and buckled patches stay buckled if wartime mechanics left them that way. The physical distortion of the airframe provides data on the impact forces it absorbed. Flattening a warped panel would erase the load path of a specific flak strike and falsify the record. The engineering challenge is ensuring that this highly damaged structure can support its own weight indefinitely without further collapse. The aircraft survived the operational theater, but the timeline did not end in 1945. How did decades of subsequent unsealed storage and unregulated museum handling compromise this carefully preserved baseline condition? The operational timeline halted after the war, when the bomber was saved from destruction, disassembled, crated, and returned to the United States. In 1960, the U.S. Air Force officially transferred Flak Bait to the Smithsonian. Most of the aircraft remained in storage, while the forward fuselage was selected for public museum display when the National Air and Space Museum opened in Washington, D.C. in July 1976. That split introduced a new layer of change driven by presentation rather than combat survival. To prepare the nose section for exhibition, technicians followed the display philosophy of the time. The prevailing doctrine treated museum aircraft as objects that should appear coherent, clean, and visually uniform. Bare aluminum, corrosion, peeling paint, and degraded surface finishes were considered unsightly defects rather than primary evidence. To correct those perceived flaws, the forward fuselage received layers of overpaint that masked the weathered wartime surface beneath. The treatment improved the display appearance, but it also obscured the physical authenticity of the aircraft. Modern conservators now treat the 1976 display preparation as a later intervention that must be physically unwound. The goal is to remove the aesthetic additions without damaging the authentic World War II surface beneath them. The decision to remove the 1970s overpaint is constrained by the fragility of the layers beneath it. The later paint sits directly over original olive drab paint, zinc chromate scab patches, graphite signatures, soiling, and abrasion marks left by wartime use. Before any removal can begin, conservators must establish the layer structure, thickness, solubility, and hidden visual evidence through testing rather than assumption. It has to be tested, mapped, and approached in controlled stages. The method fingerprint for this operation is controlled overpaint removal on the nose section. Physical scraping or abrasive blasting is not the governing approach, because any uncontrolled mechanical action could damage the original paint, the graphite markings, and the wartime wear directly below. The team maps the areas of later overpaint through archival evidence, normal light photography, ultraviolet imaging, infrared reflectography, material analysis, and solubility testing. Conservators then use carefully tested organic solvents and controlled application methods rather than broad chemical washes. A broad wash would risk moving solvent into seams, lap joints, and fragile markings beyond the target area. The work proceeds in small, verified stages, with the removal method adjusted whenever the underlying paint, soiling, or markings change. The treatment has to be strong enough to reduce the 1970s overpaint, yet restrained enough to leave the original wartime surface intact. If the chemistry or contact time is wrong, the historical paint, soiling, and graphite evidence could be damaged along with the later layer. The isolation of the nose section allows full exterior access, but removing modern additions is only the first barrier. How does the engineering team chemically differentiate the intentional 1944 operational grime from the post-war storage dust bonded directly to it? Differentiating operational grime from later storage dirt pushes the investigation beyond the visual limits of the human eye. The wartime patina is classified as primary evidence, while retirement and storage added later dust and soiling over it. Visually, these layers can merge into a similar gray particulate sheet across the aluminum skin. The geometry of the aircraft complicates the separation. Fluid leaks and exhaust staining collect around rivets, seams, and panel lap joints, while later dust can settle directly on top of them. The team uses microscopy, material analysis, and close visual documentation to establish a defensible boundary between later dirt and historically significant deposits. The purpose is to decide what can be safely reduced and what must remain as evidence of combat service. Armed with that evidence, technicians use selective cleaning. Later storage dirt is reduced only where testing shows it can be separated from the wartime surface, leaving historically significant mud, oil staining, exhaust residue, and wear patterns attached to the fuselage. Clearing the upper debris layer exposes the condition of the underlying metal manufactured in April 1943. Across the wings and fuselage, the team identified corrosion and unstable paint in areas where time, moisture, and earlier handling had affected the surface. The conservation mandate forbids stripping the skin to bare metal as a default response. Instead, conservators document the damage, reduce corrosion where necessary, and stabilize or reattach fragile paint after testing compatible materials. The visible history remains in place while active deterioration is slowed. This rigorous stabilization process also preserved one of the aircraft's most important visual records. Flak Bait still carries D-Day invasion stripes applied for the June 6, 1944 invasion. The markings are rough, irregular, and visibly functional rather than decorative. Their uneven brushwork, paint wear, and survival beneath later surface history support the interpretation that they are wartime operational markings, not a later attempt to beautify the aircraft. Conservators continue to study and preserve these stripes because they may be among the rarest surviving original invasion markings on any aircraft. With the authentic operational markings exposed and protected, the exterior surface geometry is chemically mapped, cleaned of modern interference, and secured against further atmospheric decay. With the aluminum skin stabilized, the metal shell becomes only the exterior barrier. How does the engineering team stabilize the fragile, rapidly deteriorating organic materials hidden inside the unsealed nose compartment that cannot survive chemical liquid consolidation? Replacing deteriorated organic material restores visual completeness, but destroys the forensic timeline. Stabilizing the existing weakened threads preserves the historical artifact, but leaves severe physical vulnerabilities. The engineering team must navigate this trade-off edge inside the unsealed nose compartment of the aircraft. The team confronted extensive insect and condition damage within the forward sections. The original interior includes 50 fabric insulation panels mounted along the forward fuselage. Most are fulled wool, backed with cotton batting, and machines sewn around perforated aluminum support strips. During storage and earlier display history, pest damage and environmental exposure left losses, fading, weakened edges, and detached fragments across the interior geometry. A conventional aviation restoration would remove the destroyed batting and install modern replica fabric for visual uniformity. Here, the trade-off moves in the opposite direction: retain as much World War II material as possible and adapt textile conservation methods to secure the bomber interior. The treatment does not depend on replacing the panels wholesale. Conservators develop 3 stabilization paths. Larger losses can receive laser-cut fabric fills shaped to the original voids. Smaller losses can be integrated with needle-felted wool fibers. Where the original textile is too fragile to carry itself, a lining support can hold the remaining traces in place. The new material is made visually subordinate to the original fabric, so the repair stabilizes the panel without pretending the damage never happened. Moving to the exterior, the fabric-covered control surfaces present a related but distinct material failure. Original cotton-doped fabric survived on parts of the airframe, but age, oxidation, and shrinkage left it fragile, curled, and vulnerable to loss. Stripping the control surface and applying new aircraft fabric would solve the structural failure visually, but it would destroy original wartime paint, combat damage, and embedded surface evidence. To avoid that loss, conservators developed a support system for the original doped fabric. On the rudder, the old fabric was faced so it could be safely removed from the structure, while the aluminum framework was cleaned and corrosion was reduced. A modern Seconite 102 lining was then applied as a stable support layer. Synthetic resin was built up on the lining and the inner surface of the original doped fabric, allowing the original material to be placed back and heat set into a strong but reversible bond. Losses were filled, oxidized surfaces were protected, and in-painting was limited to the repaired areas. The stabilization of the interior wool panels and the exterior doped fabric surfaces closes 2 of the most fragile material problems on the bomber. The known components are mapped and stabilized in stages, yet the process of separating floorboards and unbolting internal bulkheads to access these areas exposes hidden cavities deep within the primary load path. How does the engineering team evaluate unauthorized foreign objects discovered wedged inside the structure that appear on no official maintenance record? Extracting a discovered foreign object provides complete material classification, but preserving its exact resting place locks the trajectory geometry in the surrounding structure. During the systematic disassembly of the forward fuselage, conservators separated the interior decking to inspect the hidden structural frames. When they unbolted the wooden floorboard panel located precisely beneath the radio operator's seat, they encountered an undocumented physical anomaly. Wedged tightly into the original timber was exactly 1 German round. This projectile does not appear in any official maintenance log or post-flight battle damage assessment. It bypassed the wartime ground crew inspections and remained undetected through decades of unsealed crate storage and subsequent museum display handling. This discovery turns the round into contextual evidence, not a loose object. Extraction could support closer classification, measurement, and metallurgical study, but it would separate the metal from the timber that recorded its strike path. The central question is not simply what the object is, but what evidence would be lost if it were removed. Following that evaluation, the team chose to leave the round in place. The mechanics of the impact dictated this preservation choice. The wood around the object holds the context of the strike, where the metal stopped, how it entered the panel, and how it relates to the aircraft interior. Mechanically prying the object loose would destroy part of that context. To offset the loss of full extraction data, the team documents the object and its location as part of the aircraft's preserved material record. The floorboard and the embedded round are managed together, not as separate display props. With the external markings mapped and the undocumented internal artifacts locked securely in situ, the isolated components are prepared for final integration. As the team transitions from component stabilization to full structural reassembly, what final operational baseline emerges when thousands of preserved effects are permanently integrated back into a single static airframe? What we can verify now is an aircraft being preserved toward a full static reassembly, with combat wear and post-war treatment history treated as evidence. Missing pieces, warped panels, patched skin, worn paint, dirt, and overlapping field modifications remain intentionally unrestored. The physical reassembly of the Martin B-26 Marauder at the Mary Baker Engine Restoration Hangar defines a new boundary for aviation preservation. The bomber is managed as an integrated forensic time capsule, not a broken machine awaiting cosmetic repair. By retaining battle damage, wartime dirt, and later evidence where appropriate, the Stephen F. Udvar Hazy Center establishes a standard in which structural imperfection is the primary evidence. The airframe is being prepared to stand as a physical document of wartime service, not as a factory-fresh bomber. The preserved damage provides direct physical insight into the operational constraints managed by the wartime crew. The B-26 was engineered as a fast-medium bomber, with wartime descriptions commonly placing its performance in the high 200s to low 300s miles per hour range and its bomb load around 4,000 pounds. Achieving that performance assumed a comparatively clean aerodynamic profile. The preserved exterior features hundreds of crude field modifications. Buckled aluminum patches, uneven fabric repairs, and irregular rivet lines introduced drag and disrupted the aircraft's intended smoothness. The physical evidence shows that ground crews and pilots repeatedly traded ideal performance for immediate structural survival, pushing a damaged airframe back into service mission after mission. Integrating these degraded components into a single, cohesive display generates significant physical constraints. During the reassembly phase, the engineering team must align wings and fuselage sections that have aged, been handled, and been stored separately for decades. Combat perforations and field repairs complicate the original load paths. Because the airframe is historically damaged, it cannot be treated as a new aircraft structure. It must be supported for static display in a way that protects fragile skin, patched areas, and original attachment points. The mechanical connections securing the wings to the fuselage require restraint and precision. Forcing misaligned parts together would induce new stresses in stabilized aluminum and fabric. Technicians document the joining points, adjust supports, and bring components together only within the tolerance of the preserved structure. This slow, deliberate process allows modern support engineering to protect the aircraft without erasing the geometric distortion it acquired through combat, storage, and preservation history. The final condition of the aircraft is entirely static. No engines will run, and no flight control surfaces will move under hydraulic pressure. Its successful stabilization demonstrates that competence in historical preservation is not measured by returning a machine to flight. It is measured by the discipline required to freeze a decaying structure in time, securing the raw evidence of its survival for future analysis.